Hello everybody, welcome back. This is a video for problem 6 for my spring 2020 final exam. Here we're going to use a Laplace transform technique to solve an initial value problem. Namely, here we have a second order differential equation and we want to find a particular solution. We've been given initial values. And so we just need to use some of our knowledge of how to compute Laplace transforms, both for particular functions like e to the 2t, as well as for derivatives of functions. So let's begin. So we're going to apply the Laplace operator to this differential equation. And when we do that, we'll get, of course, L of the second derivative. And since it's a linear operator, we can break this up, plus L of y. And this is going to equal the Laplace of e to the 2t. Okay. Now we have a formula for the Laplace transform of a second derivative. So this is going to be s squared times the Laplace of y minus s times the initial value of y, that is y at 0, minus the initial value of the derivative of y. All right, so this piece here, that was our L of y double prime. And of course, we still have a plus Ly, and well, that's not going anywhere. We don't really have a formula for that particularly other than the definition, which won't be very helpful at the moment. Okay, on the other side, we're taking the Laplace transform of e to the 2t, and we have a nice formula for that. This is going to be 1 over s minus 2. Of course, you should always think of exponentials as just being shifts. So in this case, you're shifting 1. The Laplace transform of 1 was 1 over s, and the shift is by 2. So you replace 1 over s with 1 over s minus 2. Okay, so what's the goal now? Well, we can insert these values, right? So y of 0 is 1. So that's pretty nice. And y prime of 0 is 0. So that piece is just going to go away. And what I would really like to do is solve for L of y. So we're going to solve for Ly. So let's see, how many Ly's do I get? Well, I have s squared and one more. Okay, what else do I have on that left-hand side? Well, I have a minus s times 1. Okay, let me toss that to the other side. So when I toss it over, it becomes a plus s. And then we have plus 1 over s minus 2. Okay. I can now really isolate L of y here. So I'll divide by s squared plus 1. And when I do that, I get Ly equals, now see this first piece will be s over s squared plus 1 plus 1 over s minus 2 times s squared plus 1. Okay, so we now really truly live over in the frequency domain. We've solved for Ly. We want to get our y out, which means we want to be able to take an inverse Laplace transform of both sides. Now, the first piece is all set to go, right? I'm super happy when I see this s over s squared plus 1. In fact, that's why I didn't combine these. It's because I know this piece, this is equal to the Laplace transform of cosine of t. So that's all ready to go. But this second piece, maybe not quite ready to be done with that, right? So I'm going to want to break this up, and I'm going to use partial fractions to do so. So let's come over here, take 1 over s minus 2 times s squared plus 1, and we're going to want to break that up into two pieces. We have an s minus 2 piece, and since s squared plus 1 is an irreducible quadratic, we can't factor this over the reals. We just have to leave it as s squared plus 1. However, in the numerators, well, okay, we get a constant over the linear piece, but over a quadratic, right, we need to have our own linear piece, so some bs plus c. All right, we can clear denominators, multiplying through by s minus 2 times s squared plus 1. So I'm going to multiply by s minus 2 times s squared plus 1, and that'll give me 1 equals a times, well, the s minus 2's will cancel, and I'll get s squared plus 1. And then over here, I'll have bs plus c times, now the s squared plus 1's cancel, and I get times s minus 2. All right. I'd like to find, well, let's see. How about I look at the s squareds first? So how many s squareds do I have? Well, on the left-hand side, I have 0 s squareds. On the right-hand side, I have a, and then a b s squared, so a plus b. And so I'm able to conclude that a plus b is equal to 0. Or if you like, b is going to be the additive inverse of a. All right, what else do I get? Well, if we look at just the s terms, so I have no s's on the left. Okay, the a part doesn't give me any s's. Then I have bs times -2, so it'll be -2 bs's. But then I also get c times s, so plus a c. Okay, and so we conclude that -2b plus c is 0, or if you like, c is equal to twice b. And we already know that b was the negative of a, so this is -2 times a. All right, well, we still haven't figured out any one of them particularly, so let's go to the last piece, which is the constant terms. So I have 1 is the constant on the left, and on the right, I get a times 1, and then I also get -2c. And so we know that 1 is equal to a minus 2c, but we already worked out that c is equal to the negative of 2a. So I can rewrite this as a minus twice the negative of 2a. All right, so this becomes minus minus, which is plus. 2 times 2 is 4. A plus 4a is equal to 5a. And so dividing by 5, we get a is equal to 1/5, which tells us that b, which was negative a, is equal to negative 1/5. And c, well, c was negative 2a, so c will equal negative 2/5. Okay, so that means we can rewrite this fraction over here as what? This will become 1 over 5. Okay, that's our a times 1 over s minus 2 plus, all right, now in the numerator, we're going to have a fifth and a 2/5, not to mention negatives. Let me pull those out, all right? I'll just leave the 1 and the 2 in there. So I pull out a negative 1/5, and on top I'll get s plus 2 over s squared plus 1. All right, so this constant 1/5 doesn't really bother me a whole lot because, again, I know the Laplace transform is linear. I can pull constants inside and out. Okay, well, let's look at these individual pieces. So 1 over s minus 2, heck, along the way we figured out that that was the Laplace transform of e to the 2t. So I can just rewrite it now as the Laplace transform of e to the 2t. Okay, what about this last bit? Well, it's almost pretty good. It looks a lot like this first one, except there's this lousy plus 2. Okay, but what I can do is break this up further. I can write this as s over s squared plus 1 plus 2 over s squared plus 1. And then just because I'm looking ahead a little bit, let me write this 2 on the outside. Because now, s over s squared plus 1, that's the Laplace transform, again, of cosine of t. And what about this 2 times? Well, again, we ignore the 2, it's just a constant. But what about this 1 over s squared plus 1? Well, that's the Laplace transform of sine of t. Okay, and so we've pushed everything, we put everything into the Laplace format, so let's rewrite it nicely. So Ly equals, so first we have the Laplace of cosine of t. Then, let's see, we have 1/5 the Laplace of e to the 2t. So plus 1/5 the Laplace of e to the 2t. Now let's see, we have minus a fifth times the Laplace of cosine of t. Now we could rewrite it, but why not just combine it, right? We had one of them already. We're going to subtract 1/5 of them. So we're left with 4/5 of them. And then the last piece, we have minus a fifth and then 2 times the Laplace of sine of t. So we'll get minus 2/5 the Laplace of sine of t. Okay, so now we want to apply the inverse Laplace transform. On the left-hand side, that will just give us y, which is what we're looking for. And on the right-hand side, we get to get rid of all of the l's. So we'll have, let's write the exponential first. And in fact, we could even pull out a fifth to make this look a little nicer. So we have a fifth times e to the 2t. And then, let's see, we're going to have 4 cosine of t. And then we'll have minus 2 sine of t. Not too bad. Not too bad. Hooray for the Laplace transform.